Okay, so we have been talking about we just been talking about these non-terminating and terminating systems where we're simulated by these transient simulations and steady-state simulations, and we review the formula that you use in lab 9 for the transient simulations, choosing the number of replicates, and then we're going to talk about specific cases of what they're on steady state. So that's kind of the goal here today. And just standard announcements here. So lab schedule, there's only one board lab. This lab, it's graded out of 30 as usual, but there's 50 points possible. So there is almost like 2/3 of a bonus lab added onto it. This will be due, the normal due date is, so technically the lab is assigned Wednesday, we do Sunday, but I added another week of availability to it because it's got the extra points possible. So if you want to turn it in by the due date, that's great. Get it out of the way. But if you want to take extra time to work on these bonus points, then you've got that extra week of availability that you can upload that. But I can't extend it any farther than that because it is a longer lab, there's more points. It's already hard enough for the TA to keep up to date with the normal labs. And so in order to get everything graded by the end of the semester, we really have to have that in. The labs sort of split up into a section on sequences, which if you have complex patterns of stations in your simulation setup, and sometimes you might go from one station to another station, sometimes you might go from one station to another. So if you want sort of flexible handling to move things around, these sequences help to do that. That's part one, is kind of all about that. Part two is about batching, signaling, and holding, which we talked about batching and kind of a muffin oven. This showed you how to do it inside Arena. And signals and holds are really powerful and useful tools in Arena. So even if you don't decide that you want to do all of the lab to get the bonus credit, I still recommend you at least take a look at signaling and holding, because that ends up being just a useful general purpose tool for these sims. This part two also talks about the process analyzer and OptQuest, which are two tools that may be useful in your final project, so that you don't have to manually run a bunch of simulation replications. This can automate running through a process that you kind of set. Like you say, we'll run 10 replications under these conditions, 10 replications under these conditions. Whereas OptQuest, you say, I want to minimize or maximize this particular output variable, and you figure out how to run the replications to do it, and it will automatically figure that out for you. So two powerful tools there. After this lab is done, there's still time left in the semester, so basically the lab time is meant to give you more time to work on the final project. Final project, the next deliverables here are in the last week of classes. So the Wednesday and last week of classes, that's when everyone's presentation video, basically a 10-minute video, is uploaded to Canvas, as well as a 4-page final report, where the structure of that report is on Canvas and online. You'll upload that, and then at the end of Wednesday night, everyone will get randomly assigned one presentation to watch and one final report to read that's not their own. And you'll go through and watch that and read that before Saturday of that week, so Saturday before finals week, and you'll fill out a rubric that based on the one that you watched and read, and the a sentence or two of constructive commentary, if not more. And then I will go through and take a look at your peer reviews, and I'll give you your grade on whether you've left a constructive peer review. And then I'll also look at your numerical peer reviews and aggregate them, and that will become a part of the final score for the reports and the presentation. So that's the next thing to worry about, which is not until the final week of classes. So hopefully between now and then, you're working effectively with your group to move towards getting a simulation model up and running, and these deliverables will be there. All right, so other assignments, there's this ICA-L, which is due roughly in 2 weeks before lecture L. And then after that, the only other ICA is this final exam review ICA, due for lecture M, which is our final exam review lecture. It samples from all the post-midterm ICAs, so it's similar to the practice ICA for the midterm. They take it multiple times, 5 grades recorded. you can, if you want to go back to the midterm version, the kind of practice version of all the stuff pre-midterm, I've got that available as a practice exam. But then this will also be available after it's due. It'll be turned into a practice exam, so that after that review lecture, you'll still be able to take it if you want that to have extra practice. There are sample final exams on Canvas, kind of same format and style as the midterm. Only other assignment we're about is homework J2, which is an arena-based homework assignment. You don't have to use the process analyzer, but we can help. We simplify some of the tasks that they ask for, or maybe even off quest. There will be a solution set for this one. It's a little bit more open-ended. It's kind of like a lab assignment, because we in the past used it as kind of an ABET measure. So for seeing how well people are pulling everything together. All right, so those are the next 24. Any questions?
Professor, can you hear me?
Online or in person? I see that there are some comments about audio being distorted. Let me see if I can improve that a little bit. Hopefully this sounds a little better. The captions are coming through clear here, so I'm hoping things sound fine. Okay, let me just make sure I'm hearing the right mic. Let me get my. All right, so hopefully online you can, that sounds okay. Again, I'm seeing clear captions on my side, so hopefully the audio is cleared up now that I've switched to a different pod here. I'll double check that that it's using the correct device. Yeah, I don't see any indication that it's not. Okay. All right, so then in that case, let's move on to kind of review of what we're talking about. We're now into interval estimate territory. So this is so basically now, instead of anytime you run a sim, I want you to resist the temptation of giving me just a mean for an output. So don't tell me just the average waiting time for a customer or the average queue length or anything like that. Try to capture that with an interval estimate, because every time you run that sim, you're going to get a different average. So the average itself from the samples from the sim is not as meaningful, but the interval is useful because the interval most likely captures the true average within it. So the interval is much more helpful of a quantity. Now, there are a bunch of different intervals that we can choose from. If your data are independent and identically distributed, IID, and you have more than 5 samples, then the basic interval that you can always use in that case is just using the standard error of the mean, which is just the sample standard deviation divided by square root of the number of samples. That gives you the half width on this interval. It's kind of crude. It doesn't have as much interpretability, but it at least tells you, roughly speaking, if you were to run the simulation over again, how likely would the sample mean be to be close to the previous one. Now, if you can say that your data are normally distributed and IID, in that case, and a lot of times you can say that coming out of simulations, then you want to use a confidence interval, specifically usually a 95% confidence interval, which really just scales the standard error by a critical t value. And that can be very useful, as I'll illustrate here in a second. If your data are IID but not normally distributed, one of the things you end up having to sometimes do is you'll transform the data into another form that are normally distributed. So a lot of times you don't have normally distributed data, but you might log transform the data, just run it through a logarithm, and you find that after you run it through that map, then it'll end up being normally distributed, and it meets the conditions of being able to use a normal confidence interval for. If your data aren't independent. So you've got one customer, another customer right after them, so their data might be coupled together. Then even though you've got a bunch of data, like 100 customers on one day, it's possible that all their data are so coupled together that really they're just repeated measures of a single sample. They're just repeated measures of that day. So if they're not independent, we refer to that as them being pseudo replications. So it's like taking multiple samples from the same person. And so we would usually probably have to treat them like a single individual. So if you took their average, you'd say, well, that's not an estimate of the population mean. That's just a measure for that day. And now I'm going to have to come back on a different day and get another average, and that'll be a measure for that day. So I'll need to actually replicate across days because I can't replicate across people because the people are coupled together. So that's what we kind of mean by that. So independence and normality are two things you really have to think about when you're ever taking data. So how can we interpret the 95% confidence interval? Can we make that a little bit more salient? And so I've got a little demo here where, you can just do this yourself in Excel or Google Sheets. And so I'm going to zoom in on these different areas here, but it's basically a spreadsheet where I've sampled from, in every row, I'm going to take 8 samples from a normal variable. So 8 normally distributed samples, and I'm going to have a whole bunch of rows. And then each row is going to calculate a confidence interval for those 8 samples. So how do you sample from a normal random variable inside Excel? You use the inverse transform method. This is the documented way to sample from a normal random variable in Excel. There is no norm samp function or something like that. There's a norm inv, and then you run rand into norm inv. And in that, the norm inv takes the parameters, which here are the mean and I think the standard deviation of the normal random variable, and you just run a rand, which produces a randomly distributed number between 0 and 1, and it runs it through the inverse, and that's how you generate samples from a normal distribution in Excel, just using our inverse transform method. And so I draw however many samples these are here, and I'm going to do that multiple times. So each row is like an experiment where I only gather a certain number of samples, and I'm going to run that experiment multiple times to see how the confidence interval works. So that in my columns, I actually go through and calculate a confidence interval. So I've got a column for the mean, I've got a column for the half width, and that I've got a column for the standard deviation. So you can use the standard deviation to generate the half width. So this is all how I'm just calculating a confidence interval every row. So this row samples generates a confidence interval. This row samples generates a confidence interval, and so on. And then for I know the true mean, it's 5. So I've got another column here, which just checks to see with true or false if the mean is actually in that confidence interval. And so it's just going to, like, again, I'm going to run however many experiments here, say 1,000 experiments or 300 experiments or whatever. And I'm going to ask, of the 300 confidence intervals were generated, how many of those confidence intervals actually included the real mean? And what I hope you'll see in when I show the results here is that none of the sample means that are calculated are going to be exactly 5. They're all going to be close to 5. But so if I were to say, what is the mean of this population just from data, I will never get 5 out. I'll just get a number close to 5. But if I give the interval, then more often than not, my interval will include 5 in it. So, so that's what is generated down here. And so this is on this projector, it's a little hard to see, but this is the row for 5. So this line over here, that's where it says 5. And each one of these vertical bars are a confidence interval that is calculated from these experiments. And so what we see here is that most of these confidence intervals include 5 in them, but none of the center of each one of these bars represents the actual mean estimate, the point estimate. So if you just took the mean, that's what it would give there. And you can see that those are all over the place. And so there's really, if I just gave the point estimate, I'm not ever going to get 5. So 100% of the time I'm going to be wrong. But if I give the interval estimate, then aside from a few examples here, I think I'll highlight them, there's a couple of rows here whose confidence interval did not include the true mean. But most of them, so like 97% of them, included the true mean. So if you just report a confidence interval, you'll be right like 95% of the time. If you report a mean, just a point estimate, you'll be wrong 100% of the time. And that's what I'm kind of demonstrating here. And so I want to walk through that with a couple more examples here. So that's kind of just a little thing that I put together in Excel. So we can zoom in and explore that a little bit more. So here I've got, this is 100 experiments, and I ran those 100 experiments 3 times. So it's basically 300 independent experiments. And I've chosen a low alpha, so a low false positive rate. So this is an alpha of 0.001 in all 3 cases here. And so the confidence intervals that I've generated here are effectively 99.9% confidence intervals. So each one of these blue vertical bars represents a 99.9% confidence interval. And so, like I said, I've got 100 in each one of these. The true mean is 5, it's across here. And so we can see that my 99.9% confidence interval always, in all 300 of these experiments, included the true mean in it. But it's pretty big. So that's another key point I want to hear. As you increase the percentage in your confidence interval, like in this case, this is almost 100%. The confidence interval gets really big. And what that does is it helps ensure that almost all the time, the mean will truly be inside the confidence interval. The downside is you have very little sensitivity. So the true mean, like I could report any one of these confidence intervals to someone, and I really can't say that I have any confidence that the mean is on one side of the confidence interval or another. Any one of those values in the confidence interval is fair game for the mean. So as you increase the percentage in your confidence interval, you do increase the probability you'll capture the true mean, but you also reduce the resolution of your experiment so that you really can't pin down a neighborhood of where the mean is. So what we can do is create a narrower confidence interval by increasing our false positive rate. So by increasing alpha, in this case to 0.05, so if you could read that, it says 0.05, 0.05, 0.05. So that means that each one of these are 95% confidence intervals. And there's just basically 300 of them just distributed across 3 boxes here. So 100 experiments, another 100 experiments, another 100 experiments. And what we see here is that each one, if I compare this to the previous slide, they've gotten a lot narrower. And that came by increasing my false positive rate. Now, what does increasing your false positive rate look like in terms of a confidence interval? It means that more confidence intervals are going to be away from the mean. So these ones that are colored differently, one here, 1, 2, 3, 4, 5, 6. So about 6% of these experiments, 1, 2, 3, 4, 5, 6, about 7% of these, and 1, 2, 3, 4, 5, 6, and about 7% of these. So roughly about 5% of experiments generating a 95% confidence interval fail to capture the true mean. But 95% of them do capture the true mean. So, and although I might fail 5% of the time, now my resolution is reduced. And so when I report a confidence interval, you can be fairly confident it includes the mean, and it is much narrower, so it excludes a lot more options. So I actually can get a better idea of where the mean really is. So that's kind of the good thing there. Now, if I create a very high false positive rate, so in this case, this is an alpha of 0.6. So then these are 40% confidence intervals. So they're really narrow. So on one hand, they look great because they're like, wow, you know, you've made these really sensitive. But the downside is they're not accurate at all. Because what we're saying here is only 40% of the time does the confidence interval actually include the true mean. So if I give you that interval estimate, 60% of the time, the actual mean is going to be somewhere outside the interval. So that's the fundamental trade-off there. And it's the same trade-off we see between type 1 error and statistical power in that ROC curve. As you increase alpha, you do make things more sensitive. So you make these confidence intervals narrower. But the downside is there's less likely, they're less likely to actually include the true mean. So that's what happens And so we're just translating all the stats that we've done so far into kind of interval speak, because for the rest of the semester, we're going to try to summarize our results as intervals as much as possible. Now, the other thing I can get out of intervals is if I add samples for the same false positive rate, then I can narrow the interval size. And so here I've got an alpha of 0.05. So these are all 95% confidence intervals. But up here, I have 20 samples. In the middle, I have 200 samples. And down here, I have 2,000 samples. And so what we can see is regardless of how many samples I've got here, my confidence intervals always have about a 5% false positive rate. In other words, 95% of the intervals capture the mean, even when the intervals are super tiny, like down here. So this is really showing us that one way we get more statistical power is by taking more samples. And what does that look like in terms of an interval? Taking more samples makes your confidence intervals tiny, small. So if someone needs a smaller confidence interval, like in lab 9, you say, well, okay, what I can do for you is I can, if I have the resources, I'll go out and run more replications. I will generate more data. And by adding in that new independent data, that will reduce the size of my confidence intervals so that I can give you a better idea of the true neighborhood of the real population mean, is what we see here. Now, on the other side of that, if I have the same number of samples, so here I have 30 samples in all 3 cases here, and I've got the same alpha, 0.05 in all 3 cases. So all of these are 95% confidence intervals. But what I've done here is I've changed the standard deviation of the population. I've changed the variance of the population. So here I've got a standard deviation of 0.5, here of 1, here of 2. And what this is showing is the noisier your data are, then the wider your confidence intervals get. So if there is a way for you to change your experiment to reduce sources of noise, then that will also give you tighter confidence intervals. So that might mean if you're running a physical experiment, an electronics experiment or whatever, you might need to run it in a Faraday cage to prevent, other sorts of noise to come in. If you're running if you're comparing 2 things, you might need to run a paired design like you did, or like you're doing for the ones who are still turning it in, homework G3, where you need to pair a real simulation with a simulated system using the same input data to both. And by pairing, then that ends up reducing variance. And we've got a whole section, I think unit K, on variance reduction methods. I think the next section, we're going to talk about a couple of different ways we can reduce variance in simulation. So we're not going to change the fundamental system any, but we're going to change how we run the experiments to reduce the variance. So if the fundamental system has this amount of variance, if we're smart about how we run the experiment, we can manage to explain away much of this variance. So the only variance we're left with is the variance we actually care about. And that will end up giving us tighter confidence intervals to make it easier for us to find the true effect of our simulations, our intervention 1 versus intervention 2, or our real versus simulated. So those are the 2 effects I wanted you to see. More samples makes things tighter, more variance widens things up here. So any questions about confidence intervals? About all of these properties here and how they relate to things like t-tests? I just realized I didn't open up the anonymous question tool. So I'll go ahead and do that. All right. So where does, I'm sorry, was that, I thought I, okay. So where does all this come from? So the half-width formula looks a little funny. So the half-width formula is down here. This is the half-width formula here. Here is basically a t-test. So we all know how to do a t-test now. We calculate, we have a 1 sample t-test. So we've got a hypothetical mean. We've got our sample mean from data. We calculate this t statistic here. We compare it to a critical t value. And with that, we either reject mu or don't reject mu. And so we could say, well, is there another way I can represent the t-test? And so I could say, well, what if I'm in the case where my sample mean is above my hypothetical mean? Well, that allows me to get rid of these absolute value signs and just algebraically rearrange these things. And so when the sample mean is greater than the hypothetical mean, then this condition here translates into this condition here, which after rearrangement translates into this condition here, which basically says that it's equivalent when the sample mean is greater than the hypothetical mean. That's equivalent to saying that the hypothetical mean is less than the sample mean, but is also greater than the sample mean minus our half width. So the half width formula kind of gives you 1/2 of, it's saying in this condition, that's where the hypothetical mean is going to fit in the confidence interval. On the flip side of that, under the case of if my sample mean is less than my hypothetical mean, I do the same algebraic rearrangement, and I find that this particular case is equivalent to the hypothetical mean being in the upper side of the confidence interval, bounded below by the mean and above by the upper side of the confidence intervals. So what we see here is that this condition up here with the absolute value, saying this condition, saying what are the mu such that this condition hold? That's equivalent to just specifying the confidence interval. The mu for which this condition holds are the mu that go from this x minus the half width all the way up to x plus the half width. So these are all of the hypothetical means that a one sample t-test would fail to reject. That's what a confidence interval is. Any questions about that? See that that's where we get the half width formula. And that's the reason why all of the assumptions we need for the t-test, we also need for using the 95% confidence interval. They need to be independently distributed and normal. Okay. Questions online? All right. So the confidence interval here, put another way, is the probability that the hypothetical mean is within the confidence interval will be 1 minus alpha. So if the alpha is 0.05, 1 minus alpha is 0.95. So the probability, if you calculate a confidence interval from data, the probability the population mean is actually in it is going to be 95% in the case of an alpha of 0.05. So if the confidence interval does not include your hypothetical mean, we don't have to run a t-test. We know that p is less than 0.05. We know that that hypothesis that's outside the confidence interval is rejected. So confidence intervals are a geometric interpretation of a t-test. Now, what's nice about that is you can also take multiple one sample confidence intervals, combine them together to do two sample tests. So if two one sample confidence intervals do not overlap, then we know that if you were to do a two sample test on those data, comparing one set of samples to another set of samples to ask if they have the same mean, then if their two one sample confidence intervals do not overlap, so there's air between them, there's daylight between them, then we know that the two sample test would also have a p less than 0.05. The two sample test would say these two populations are different. They have a different mean. So, so that's kind of our two sample rule here. Now, if somebody gives you a standard error of the mean instead of a confidence interval, and you want to quickly do a two sample test, if you have a good reason to believe that the data are normally distributed, you take this SEM that they gave you, and so long as they have more than, I don't know, 10 samples or something like that, you can assume that the half width is just twice the SEM. So sometimes data are listed with their standard error, and so you just double their standard error of the mean, and then you get the confidence interval half width. And then without even running a t-test, you can do the effect of a two sample t-test on those populations, or a one sample if that's the question you're going after there. So these are quick ways to look at data summary statistics and run stats without actually having to do the math. So the example I had for that is
if we've got this experiment where we had a control group and a treatment group, the response variable was enzyme activity. Doesn't matter what the response variable is here, but we know the control group had this mean. And in this case, it's standard error. So this is representing the mean plus or minus standard error bars. The treatment group has this mean plus or minus standard error bars. Although it looks like these error bars have daylight in between them, you could put a slice of paper in between them, and so clearly they don't intersect. We have to do this game with a confidence interval. And so if I double the standard error of the mean, so I make it so it'd be somewhere up here, and I double this standard error mean, so it'd be something down here, the estimate of the confidence intervals would overlap. And so in that case, I really can't conclude that these two groups are different from each other. I have to run a formal two-sample t-test on these data versus these data to be able to really tell that they're different. But if these were confidence intervals already and not standard errors and they didn't overlap, then I wouldn't have to run the two-sample t-test because I know that the p-value would be less than 0.05. I don't know what the p-value would be, but I knew it would be less than 0.05. So confidence intervals can help us do quick statistical tests just by looking at these things. It only really works for two groups. Once you start going to 3 groups and 4 groups, it's far more complicated. But the one sample case and the two sample case are really easy to sort of handle if someone gives you a confidence interval. Okay. So any questions about that, about this interpretation? Okay. The other nice thing about confidence intervals, if somebody gives you a confidence interval, they're also giving you the assumption that the data are normally distributed. And so if you trust them, you can look at the confidence interval and you can back out the mean. So it's just the middle of the confidence interval, the average of the two barriers of the confidence interval. And then you can also back out the standard deviation. And that's just the half width of the confidence interval. If they told you the number of samples, then, and if you know it's 95%, you can figure out what the alpha is, you can figure out what the number of samples are, and you can back out an estimate of the standard deviation. So a confidence interval is useful in that it is a graphical depiction of a t-test. It also encodes the two parameters of the normal distribution that approximates the data. And so we can figure out their mean, we can figure out their standard deviation, and we can then use a z-test, for example. So, or basically we can estimate that distribution as being a normal distribution with the mean in the center of the confidence interval and with the standard deviation according to this formula. So that's pretty nice too. So all sorts of reasons why confidence intervals are really useful to present and really compact ways to give a sort of a rich characterization of data. All right, so that's my confidence interval review. Any questions about that? All pretty confident in what confidence intervals are? Okay. The other interval we talked about was prediction interval. This is less used, but I think just as important. A prediction interval is not about estimating a population parameter. It's about estimating a distribution, a real distribution from a system. So when I run a simulation, I'm going to get 10 samples out of my 10 replications, and those samples are going to have variance. Now, if I want to estimate the true variance in the population, then the small sample size is going to itself be a type of uncertainty, which is going to inflate my estimate of the variance here. But as I run more and more samples, the true variance becomes clear. And that's what the prediction interval really is saying here, is based on the number of samples I have, this is the 95% interval of where I think the next samples are going to be. So if I need to say, like, well, based on the 10 times you've run this simulation, what is the chance that the next run will be in a particular spot of the real line? Well, the prediction interval kind of tells you, based on how many estimates we've run, where we think the next run is going to be. And so if R is really low, if you've hardly run any samples, it's going to be giant, because they're basically saying, I've only run this thing once, so I have no idea where the real where the real data are going to be. Now, we assume that we have some estimate of standard deviation, so that is going to put a little bit of a bound on it. But as I run more and more replications, I get a better idea of what the true standard deviation is. And so this prediction interval is going to get narrower, but it is never going to collapse to a point, because every time you run a sim, you can get different outputs because it's a stochastic simulation. Every time you sample from a real system, you can get different outputs because we assume there's variability in the system. So the prediction interval doesn't collapse to a point, it collapses to a distribution. It collapses to our idea of where we think the data left to gather is going to fall under. So it's very similar formula, but notice it's got the 1. It's not just simply S over square root of R, it's kind of S times 1 plus 1 over R. So otherwise a very similar interval. So any questions about the difference between prediction interval and confidence interval? Questions online? It's commonly said here, the confidence interval is a measure of error. So how likely is it that I guessed the right mean? Where the prediction interval is a measure of risk. So given the data that we have that we've already collected, what's the risk that we're going to get the next outcome is going to be in a particular range? And that's what the prediction interval helps us quantify. Okay. And then quantiles. We've talked about how quantiles are point estimators, but we need to put confidence intervals around quantiles. And so if somebody asks for what's the 85th percentile of the speeds in your traffic simulation, then we can't just say, well, it's 75 miles per hour. We have to say, well, it's somewhere between 70 miles per hour and 80 miles per hour. We don't actually know what the population is, but based on the experiments we've run, we think that the 85th percentile speed is within this range. So how do we get that range? And this is a little bit different, but it's the same kind of idea that we just talked about, where I can figure out my point. I need to figure out kind of a low range in a sorted list and a high range in a sorted list. And so I've got this half width, but it's not a half width in like value space, it's a half width in kind of like percentile space. And so if I'm trying to estimate the P percentile, so that's just going to be the P position in a sorted list of data from an experiment. Then I want to say, well, what's my lower end? At what position do I need to start my confidence interval? And that's what the half width gives you, is it says, well, if your point estimate is at the 85th percentile position in your sorted data, then calculate this confidence interval, and that will give you a number that will be less than 1, that I can take my 0.85 here, subtract that off, and that'll give me a number like 0.7 or something like that. And that'll say, go to the 70th percentile position in your list of ranked data, and that will be the lower end. And then you can add that to your original percentile, whatever your 85th percentile, and it'll say, well, that should be 90. So that'll say, go to the 90th percentile position in your ranked list. And then together, that's how you actually get that confidence interval on the quantile. And so that's why I've got this kind of like, the index here is the floor of the number of data points times this PL, and this is the ceiling of the number of data points times this PU. That's how you get the confidence interval on the quantile. So any questions about that? Confidence intervals on quantiles, a lot of aisles kind of, and percentages and things like that, going around. So it's a little hard to say, but if you think about it, it is definitely a necessity, because we don't like to just give point estimates to people. Because 100% of the time you're wrong whenever you give a point estimate. Okay. All right. So then the last thing we covered last time was, if we're running a transient simulation as a simulation of a terminating system, how many replications do we run? And you've now had some experience with this in Lab 9, and actually some kind of experience with this with homework G3. So when someone says, how many replications do I need to run? The traditional way to answer this is with a power analysis. So this is what you did in homework Z3. You get an estimate of the standard deviation. So run pilot study, generate estimate of variance, and then you use operating curves or software to estimate the necessary sample size to get a desired power. So you have to specify a desired power, a test, and our the minimum detectable effect size. So if it's really important for you to have a particular power, then you have to do a power analysis. Now, the confidence interval provides an alternative way for us to do something similar. It doesn't give us any conditions on the exact power that we're getting, but it still allows us to quantify the sensitivity of our system. So that's what we're going to see here, is that instead of telling me how much power you want and what the minimum detectable effect size is, you can tell me what's the half width you want in my estimate of a parameter. And that's very similar to doing a power analysis. Again, it's not a formal power analysis. I'm not guaranteeing any power, but it gets me kind of close to that because it's like specifying a type of effect size. This is saying that I want your interval estimate to not be any wider than this size. And that's going to say that in order for me to do that, in order for me to tell you that I'm not sure what the mean is, but it's no smaller than this and no bigger than this, and that interval is tight, then that's going to tell me how many samples I need to get that to run. So I'm going to still have to run a pilot study to estimate variance, but then I'll choose replications to meet a half width constraint instead of a power constraint. So the way that looks is I have to ensure, of course, that independence across replications. I do that in experimental design. I have to ensure normality, and that's what I need to run to do a confidence interval. The same thing you'd have to do if we're running a t-test, and that might require me to do a QQ test and a Shapiro-Wilk test, and so on. So, but once I've got that, and we normally have that in a lot of simulation data, then we get our half width estimate. So like in lab 9, we said we don't want the half width to be any bigger than X. And so that half width comes in, is that's, I don't want to be any bigger than this. I've already run a pilot study with, say, R replication, R0, R naught replications. That's what I use to generate this estimate of S. And I just do some algebraic manipulations of the half width formula to say that if I know that my estimated variance is S naught, which I got from R naught replications, and I know that I don't want my half width to be any bigger than epsilon. So it's a type of effect size. So I want the sensitivity of the test to basically be epsilon around the sample mean. Then this quantity here gives me a lower bound on the number of replications. Now, the problem is that the t value that I put in here also depends on the number of replications. And so solving for this might have to be done numerically. Like you'd have to create a column in Excel and see at what point, at what number of replications does this finally hold. The simpler way to do it is assume that you have enough replications that your t distribution is approximated by a standard normal. And under that case, it's super simple. Is you just you look up the critical z value for the desired significance level, alpha, multiply that by your pilot standard deviation, divide that by the effect size that they want, square it, and then that is going to give you an estimate on the number of replications you need. Now you've already run R naught independent replications, so you can then collect R minus R naught more replications, add them into your pool, and then hopefully you'll have a confidence interval that is less than this epsilon. It doesn't work all the time, but it's going to be pretty close. If you still are a little bit bigger than this epsilon, you can still gather a little bit more data, but most likely you'll be pretty close to this epsilon and not that far over it if you follow this procedure. So are there any questions about this? This is far simpler than a power analysis. And it's usually easier to communicate to someone because you say to someone, I can only give you an interval of where I think the mean is. So they say back to you, all right, just make sure the interval is no bigger than this. And that no bigger than this is what allows you to then figure out how many replications you want. And note that's a half, that epsilon is a bound on the half width. So the whole interval is 2 epsilon sized. Questions on that? Again, this is something you hopefully played with in lab 9. Okay. All right, so what's the downside of increasing replications? Why don't I always just run 1,000,000 replications? You may not have felt this in a lot of your labs so far, but as the labs get more complicated, hopefully you've seen that. Well, I don't know. I mean, those of you who've used the remote machines might know what I'm talking about here. So what's the downside on running a lot of replications? The practical downside. Anybody? Why don't you want to run 1,000,000 replications? Yeah. Right. In the real world, if you're running experiments out in the real world, for sure. But even in sim, what's the downside? That's right. So in the real world, it costs every time you run an experiment. Every replication is dollars, right? It could be $100, could be $1,000 per replication. In the computer, every replication is time. And so as you run that call center simulation or whatever, the first time you run it, it might take 30 seconds to run one replication. So you could say, well, yeah, if I just run 1,000,000 replications, I'm going to get really tiny confidence intervals, and I'll have a great estimate of the average wait time or something in a call center. But 1,000,000 replications with each a 30-second time, it takes a long amount of time to get that done. I have a project I work on now with wetland configuration and optimizing that. And every time I put in a new wetland configuration, the computational tool that sort of sees how well that configuration worked when it's implemented in this river valley in Texas takes about 10 minutes to run. So there's 982 different wetlands that I can place, and I can place any subset of those. So that's 2 to the 982 positions in my decision space that I have to optimize over. And every time I choose one of them, it takes 10 minutes to evaluate in simulation. So that's an example of that. I can't run I can't run 2 to the 982 simulations for one, but even if I choose to run 100 of them, that's 100 of them times 10 minutes each. So that's 1,000 minutes just to run that tiny experiment. So we would like to use as little replications as possible. And so that's why we don't just sort of say always run 1,000. We typically want to run, like, really ask yourself, what half width do I want? What's the variance in my system? And if I can get the half width with fewer replications, then maybe do that, because a complicated sim can take a very long amount of time. Okay, so any questions about that? That's kind of like why we have this formula, this thing down here, that computational budget is a big deal. All right, good. So that was transient simulations, which are for terminating systems. So let's do a quick attendance exercise. The questions here on the slide here, but this is just testing us on what we remember about confidence intervals. For the same set of 5 samples of normally distributed data, which of the options below corresponds to the largest confidence interval of the mean, or on the mean? A, 1%, B, 10%, C, 85%, D, 95%, E, 99%, or F, I don't know, it depends on the data. So which one of these has the biggest, the largest, the widest confidence interval? Or which confidence interval is the biggest interval, the largest interval? So I'll also try to put that in the chat. Sorry about that. And this is something I talked about earlier, where you're looking at the widths of the confidence intervals, and I was saying that, or another way to view it is this percentage is how often you'll be right. So in a 95% confidence interval, I am right when I give them that interval. And like the mean will be in that interval. So if I go to a 99% confidence interval, I'm right more often. If I go to a 1% confidence interval, I'm right less often. So for the same data, I'm changing the size of my confidence interval. So I'm kind of getting a hint here that it's not F, it's definitely A through E. So, but I have to figure out, which one it is. which pretty much means it's either A or E. All right, so how many people think it's A? How many people think it's E? How many people think it's something in between? All right, great. Yeah, E is what I was looking for. So that's what I'm looking for. The way you get high confidence is you make giant intervals that are almost definitely going to contain the mean. So giant confidence intervals are not useful. So you get utility out of making the confidence intervals small, but the smaller you make your confidence intervals, the less accurate they are. So there's like an accuracy utility trade-off. Okay. All right, so now I just have to do an addition here to talk about steady state simulations. So we talked about terminating sims where we care about all the data, beginning, end, in the middle. Now we're talking about non-terminating systems where we only care about the steady state behavior. And that's why we're just building steady state simulations. So our steady state simulation, when you start the sim, it has initial conditions. It just has to, when you have to start the sim somewhere. And so let's say this might be waiting time in line. It's going to increase over time because initially the system's not going to have any load. But then as the system runs, it gets more load and the waiting time increases. And eventually there's some steady state waiting level. And if we include this early stuff, which is just an artifact of the simulation, the real system doesn't go through this transient, at least not enough that we care about, then it's going to pull the estimate of this steady state here, which should be kind of the middle of these squiggles, down to where this hash is here, the hashed line is. And so that is bias that we would like to eliminate. And we eliminate the bias by making the kind of initial conditions better in some way. And so one of the ways we can do that is by introducing a warm-up period. So you've seen that in lab 9, where you have to decide how much data to cut off the front of a simulation to reduce the bias in that simulation. And then once we've decided on that, to sort of how to remove the bias, then we have the replications question. But what's different here is that because we don't care about the end time of the sim, we have another option to reduce our confidence interval size. And that's actually running our sim for longer. So that's what we're going to see here is that when do we just add more replicates of the same sim, or when do we run the same number of replicates for longer? So that's what we're going to talk about here. All right, so when we talk about steady state performance, the real variables we're trying to estimate are really things taken in the limit to infinity. So for discrete time data, if we're talking about like the wait time or something for each customer, then what we're really saying is we took an infinite number of customers, what's the limit of their kind of average wait time on them, and that's what we're kind of trying to estimate here. For continuous time data, this might be the utilization. So there's an instantaneous utilization, and I can say take the average of those instantaneous utilizations over a long period of time, and that average utilization is what I'm trying to estimate. And that parameter is really only defined in the limit as time goes to infinity. But our sims don't go to infinity. So in a finite amount of time, how do we estimate these well? And so in each one of our sims, our per replication, this is what our estimate's going to be for that replication for that performance variable. For discrete variables, it's going to be take each one of those discrete samples from within the rep and add them up together, but we're going to throw away the initial D samples because they're in our warm-up period to get rid of bias. And we're going to run the sim for N of those samples. And so N determines the end of the sim, D determines where we sort of start taking data. And we end up kind of taking this average. So technically this I think should be 1 over, I suppose, N minus D. So that's kind of a flaw there. That's fixed down here, where we're saying here that if I'm taking continuous time data, I need to say when do I start and when do I end. So I integrate from the end of the warm-up period all the way through this interval after the warm-up period, and I take the average divided by TE. And so the big question here is how do I choose the warm-up period So that's D or T naught. And how do I choose the length of the sim? And that's in the number of customers, for example, or the end time. And then also the initial conditions. So I can choose different initial conditions. And so all 5 of these things, or really 3 of these things, because this is like the continuous version of the discrete, I choose those to reduce my bias, achieve precision, and respect my computational budget. So that's what we need to say is what are methods we can use to do that? So the first thing we're focusing on here is getting rid of this bias. The common solutions to get rid of bias are either the warm-up period that we talked about in Lab 9, or something called intelligent initialization. Right now, you start your sims and all of your queues are empty. And so they have to fill up. And that's one of the reasons why you can get this rise here. So one thing we could do is let's just put individuals in the queue at the start of the sim. We don't have to wait for them to develop through this period here. And so that's what we mean by intelligent initialization. Let's set initial inventory levels to realistic values, to what we think the steady state values might actually be. Place customers in a queue. Start with some of the components already failed or in a degraded state. So when you start a reliability simulation, normally you start and all of your machines are in pristine condition at the beginning of the sim. But in reality, that's a very artificial state that only existed once in the real system's history. And we probably could have said, well, let's actually start with one of the machines almost about to fail, another machine pretty new, some machine in the middle, or so on like that, to make it a little bit more realistic in terms of a portfolio of what they've got. Now, how do you do that, like quantitatively? Well, I can collect data from a real system and say, in the real system, roughly at steady state, how many people are in the queue? And I can try to then mimic that in my sim. The other thing I can do is go into, say, like E470, go into a mathematical model and say, what would the mathematical model predict that my steady state queues are going to, like queue lengths are going to be? What a mathematical model predict that my wait times would be, those sorts of things. And then try to pick my simulation model to match the mathematical model. So this is what we refer to as using a warm start. So we can warm start up our sim using the math as our basis for that. And that should make the transients much smaller. So instead of starting from way down here, hopefully they'll be pretty close to the steady state values so that this initial warm-up period can be a lot smaller. So that's one thing that we can do, intelligent initialization. So any questions about what I mean by intelligent initialization, not just picking arbitrary initial conditions. Choose initial conditions that are close to what you think the real system has at steady state. Okay, so then the other thing we can do, which we're probably going to have to do anyway, but hopefully we can do less of it if we do the intelligent initialization, is set a warm-up period. So we have our initial conditions, and then we actually have the steady state's initial conditions, which is kind of at the end of the warm-up period. So how do we choose the length of this initialization phase? This is data that we're just going to throw away, and we only start taking data during this second phase over here. So how do we do that? Well, this is very heuristic. So the idea here is there's not a general rule I can give you. There's sort of a bunch of techniques that will hopefully do well for a lot of systems. And so one thing you can do is run your simulation, say one replication of your simulation, like these are data, I think, from Lab 9. And you can just sort of hopefully look at that, and maybe you'll see kind of an initial transient period that is qualitatively different than all the rest. Like maybe off this one replication, I kind of look at this and see, this rise here, that doesn't quite look like the rest of the system. So maybe this is where the real steady state starts and the rest of this is just transients. That's hard to kind of, it doesn't look quite right. It has so much variability out here and here. I mean, this might actually be a normal, pulse that we would see in steady state. So an alternative is to do signal processing, to do filtering of those data. So this is something that the book talks about. You can take those data that you had from a single replication And you can take the cumulative average. And so what they're doing here is they're basically producing a plot, not of the raw data, but of the average of all the data seen so far. And so here I think they've got it's hard to see in this line, but the dark lines here are the raw data, and the kind of light lines that are sort of, they're kind of just above my finger here. So in this portion, you can see the separation between them, but you can see that the cumulative average here has far less variance. And when I look at the cumulative here, I kind of see there's a little bit of a rise, and then things are pretty much the same after a particular point. And maybe that point is the point at which I call the end of my initialization period. Still not very satisfying, but we're at least getting a little bit closer. Another option is to run a couple of different replications. So 5 replications or something like that, and plot them all together. And so this again is your lab 9 data, but I'm plotting across multiple replications simultaneously. And when I do that, maybe I start seeing general patterns that about everybody starts acting roughly the same after a particular point. But what might be more useful is to then create confidence intervals at every time step. And that's what your book does. So they talk about this. And so what we can do is at every time step, I average across all of the replications at that time step, and I generate a sample mean and a confidence interval. And I can plot that here. So what I'm seeing here is the dark bar is the mean, and the upper one here is the upper side of the confidence interval. The lower one is the lower side of the confidence interval. And so now I'm plotting confidence intervals across my replications over time. And what I see here is that this kind of rises up, but then it looks like it pretty much settles out maybe around here, this time point here. So maybe that is my initialization period. And that kind of is a much better way than all of the other ways there. So run a couple of pilot replications and generate a confidence interval across them and see when the confidence interval kind of dies out. That's another way to kind of do it here. Any questions about this before I show you one that's fundamentally different than this? We're kind of building up. Like you can imagine, varying the number of replications here. It kind of starts looking like if I change the number of replications to 1, it's sort of like where we started. So we're kind of building up to this. So hopefully everybody can see is I've just taken like 5 replications, averaged across them over time. And then the kind of adding all of that together, I can then filter on top of those. And so this ensemble average curve can be further smoothed out with a smoothing window. So basically this is saying that every point of the ensemble average curve is I take it and I take 2m plus 1 of the points before it, average all those things together. And that's like a boxcar that's just moving like a train down the tracks, averaging everything under the boxcar. And then that average is then produced, will further smooth out this curve here. So if that's not already smooth enough, if you do that, then you might end up seeing a nice smooth transient period, then followed by a pretty solid steady state period. And then that will end up being, the difference between those will be where you want to put your warm-up period or after that. So it's got to be that point or later. So those are a couple of web methods that I can do that, that are based on just looking at these data. There's a related topic of autocorrelation that has to come up, kind of next here, that uses sort of a fundamentally different method to try to figure out, these types of intervals. But hopefully this makes sense so far, just averaging over replication. So any questions about initialization bias? Different ways. This is no I can't tell you for sure exactly when the best initialization period is. The longer you make the initialization period, the more data is wasted. That's the more time is wasted in your sim. But the more confidence you have that you get rid of initialization bias. Okay. All right, so now we've handled initialization bias, hopefully. If we haven't, so if there's some significant bias remains, our confidence interval will be misleading. Adding replications will not reduce initialization bias. So we really have to get rid of the number of replications before we, get rid of the bias before we start worrying too much about those, the number of replications. But if we assume that we've gotten rid of all of our bias here, a good approach to choose the end of our sim that helps to ensure that we have a lot of data that somehow is going to balance out the wasted time we've had in this initialization bias is to try to run our sim for 10 times the initialization period that we've chosen, the warm-up period. So for discrete simulations, for we're choosing, in discrete data points, we want n minus d to be greater than 10 times d. For continuous ones, where we've chosen a warm-up period that ends at a particular time, we want our end time to be 10 times that warm-up time. So that is a way that we we can't just throw out a bunch of data and then end the sim. So this helps us give kind of a pivot point that shows that we want to collect at least 10 times as much data than the warm-up period that we're throwing away. And hopefully that gets rid of all of our bias. So you choose this period based on the methods I already talked about. You choose this based on this heuristic. And then how do you choose the number of replications? Well, we then use the methods that we already talked about for terminating simulations to choose replications. And we should try to choose replications as high as possible, up to r equals 25. And so if you decide for the half-width estimates you need, that you need an R of 50 or whatever, then that's fine. You need that R of 50. But once you go above 25, we're actually going to have a slightly different strategy. So rather than running an additional 25 replications, it's better for us to actually extend the end time of the existing replications that we already have. So step 2 is basically choose replications based on what we would do for a terminating simulation. And then if that R is greater than 25, then we're going to extend the end time on all of our replications because we'll actually get more bang for the buck out of extending the end time. So what does that look like? So let's say that I decide that I want to run R minus R naught additional replications, just like I just talked about for terminating simulations. Now, I could actually run those replications, but the thought was, let's say, I decide that I'm going to run 25 reps and all the rest of them, I'm going to use this other method for. And what it's saying here is here's R naught. This is the number of replications I've chosen to already run. Let's say that's 25. Let's say R is the number of replications I would like to have in the ideal world. Let's say that's 50. Then what I'm going to do is create a ratio of the number of replications I'd like to the number of replications that I have. And I'm going to scale both my initialization period and my end time by that ratio. So my initialization phase is going to grow. My data collection phase is going to grow. And so each one of my simulations is going to grow by a certain amount of time. Because they're going to collect more data, the variance per replication will decrease. But what's nice about, and that's what's going to reduce my confidence interval size. But what's nice about this is it also actually throws out more data. And so my initialization bias will also decrease. So if you need less than 25 reps, just run the reps. But if you need more than 25 reps, you're not going to get that much benefit by running additional replications. And so at this point, you can start attacking initialization bias too. And so for that high number of replications, just take your existing 25, run them longer, but make sure your initialization phase also grows. So are there any questions about that? How we can trade replications for time and actually attack initialization bias even more? Okay. All right, so what I think we'll do is next time I want to cover batch means, which is the only thing we sort of missed here, which is an alternative approach where rather than running a bunch of replications where every replication discards data, what I'm going to show you how to do is how to run a single replication that is really, really long. So you only have an initialization phase once. And if you run it long enough, then you can create batches within the replication, which are effectively independent from each other. And this is what Arena tries to do for you. If you have the replication run long enough, it will automatically try to do this, generate confidence intervals this way. But I won't rush that. We can talk about it next time. So for now, let me just give you this attendance exercise here. And it just, I guess, read it right off the slide. So which of the following is not affected by an increase in independent simulation replication runs? Confidence interval, mean estimator, computational time, estimator bias, or all of them. So I'm saying that one of these or all of them, I guess, is not improved or affected by adding more simulation replications. Which one is it? Which one can't you deal with by adding replications? And that's all I've got for you. So otherwise, I'll see you Thursday. I'll put that in the chat if I can. Oops, sorry about that. All right, those online, there's still a good portion of you, so I'm hoping that the audio improved. Otherwise, that's all I got. If you've got any questions, I'd be happy to take them. Otherwise, I'll see you Thursday, and I will be closing the room if there aren't any. Quick question, yep. The labs, I think there's a portion of them are graded and a portion haven't been. So I asked the TA about that last week. I'll follow up with them this week to see if I can put a rush on that. Sorry about those delays. I know that's frustrating. I'll do what I can to see if I can speed it up. Okay. I'll go ahead and stop the recording at this point.